Good morning, student. Today we discuss thermodynamic principle of metallurgy. Student, thermodynamic principle of metallurgy is based on the equation delta G is equals to delta H minus T delta S. Only those reactions are feasible for which delta G have large negative value. I repeat it again. Thermodynamic principle of metallurgy based on the equation delta G is equals to delta H minus T delta S. Here delta G is the change in Gibbs free energy, delta H is change in enthalpy, T temperature, and delta S is change in entropy. Only those reactions are possible for which delta G have large negative value. Now let us discuss Illingham diagram. Illingham diagram. Student, Illingham diagram provides sound basis for considering the choice of reducing agent for the reduction of oxide by plotting a graph between delta G naught versus temperature. I repeat it again. Illingham diagram provides sound basis for considering the choice of reducing agent for reduction of oxide by plotting a graph between delta G naught versus temperature. In Illingham diagram, we plot a graph between delta G naught versus temperature. Now the simplest version of it is given. Now it should be noted, student, any metal will reduce the oxide of other metal only if it lie above it. I repeat again, any metal will reduce the oxide of other metal which lie above it in Illingham diagram, because delta G naught of the combined redox reaction is more negative. I repeat again, Illingham diagram provides sound basis for considering the choice of reducing agent for reduction of oxide by plotting a graph between delta G naught versus temperature. Any metal will reduces the oxide of other metal which lie above it in Illingham diagram, because delta G naught of the combination redox reaction will be more negative. For example, here in this case, magnesium is good reducing agent for aluminium. Now, question arises, out of carbon or carbon monoxide, which will be better reducing agent at 673 Kelvin? I repeat, out of carbon or carbon monoxide, which will be better reducing agent at 673 Kelvin. Student, below 673 Kelvin, carbon monoxide easily oxidizes into CO2. I repeat again, below 673 Kelvin, carbon monoxide is easily oxidized into CO2 than carbon to carbon dioxide. Therefore, below 673 Kelvin, carbon monoxide is better reducing agent. But above 673 Kelvin, carbon is better reducing agent, because above 673 Kelvin, carbon monoxide becomes stable. Carbon monoxide is stable, hence oxidation of CO2 is less rapid. Now let us discuss blast furnace. Students, blast furnace is widely used in extraction of iron from hematite. Blast furnace is widely used in extraction of iron from hematite ore. The systematic diagram of blast furnace is drawn like this manner. Blast furnace consists of lining of silica inside, which help to removal of slag. Here the mixture of powdered ore. Student, the mixture of powdered ore, coke and limestone is said to be charged. I repeat it again. The mixture of powdered ore, coke and limestone is said to be charged, which will be introduced from the top of the blast furnace. There are various temperature zone in blast furnace. It is 1070 Kelvin, 1270 Kelvin, 1870 Kelvin, and then 2170 Kelvin. Here the outlet for slag. Slag is the unwanted material that will be obtained during extraction of iron from blast furnace. And here is the outlet for pig iron. Here we obtain pig iron. Here the pig iron will be there, which will be obtained after treatment in blast furnace. So it is a systematic diagram of blast furnace. Here the air, here the portion where the air introduced in blast furnace, here the part where the hot air exists from the blast furnace. Here one thing must be noted: the iron obtained from blast furnace is said to be pig iron because it contains 4% carbon content, while the cast iron consists of 3% carbon content. There will be a question maybe asked in CBSE board examination. What is the difference between the pig iron and the cast iron? Pig iron consists of 4% carbon content, while the cast iron consists of 3% carbon content. The unwanted material obtained from blast furnace during extraction of iron is said to be slag. In this process, generally we obtain ferrous silicate as a slag. Now the flux. Flux are those substances which convert infusible material to fusible ones. I repeat, flux are those chemical substances which convert infusible material to fusible one. For example, limestone. Limestone acts as a flux. It should be noted basic flux is used for removing acidic impurities and vice versa. Now the question arises, what is the role of silica in metallurgy of copper? I repeat again, what is the role of silica in metallurgy of copper? Student, silica, that is SiO2, help in removal of iron oxide. I repeat, silica help in removal of iron oxide in form of slag. Example, iron oxide when combined with silica SiO2, we will obtain FeSiO3, that is called slag. So slag is the unwanted material obtained during extraction of copper. Now, question arises, why copper matte put in silica line converter? Student, copper matte consists of iron sulfide and copper sulfide. I repeat again, copper matte consists of iron sulfide and copper sulfide, which on oxidation gives iron oxide and copper oxide respectively. I repeat again, copper matte consists of copper sulfide and iron sulfide, which on oxidation gives copper oxide and iron oxide respectively, as according to the equation. Now balance the equation. Now we are balancing the equation. Now iron oxide and copper oxide further react. Now iron oxide combined with silica to form iron silicate. It is a slag, that is the unwanted material, while the copper oxide further react with copper sulfide. I repeat again, copper oxide further react with copper sulfide to give copper metal with elimination of sulfur dioxide gas. Now the question is, why copper metal put in silica line converter? Student, copper metal consists of iron sulfide and copper sulfide, which on oxidation give iron oxide and copper oxide. Iron oxide combined with silica to form slag, which is an unwanted material, while copper oxide react with copper sulfide to give copper. That is why copper metal put in silica line converter. Now we are discussing here electrochemical principle of metallurgy. Now let us discuss electrochemical principle of metallurgy. Electrochemical principle of metallurgy is based on the equation delta G naught is equals to minus NF E naught cell. Only those reactions are said to be possible for which E naught cell comes out to be positive. Only those reactions are said to be possible for which E naught cell is positive or delta G naught must have negative value. Now let us discuss metallurgy of aluminium. Students, now let us discuss metallurgy of aluminium. In metallurgy of aluminium, Al2O3 is mixed with Al2O3 is mixed with cryolite and feldspar to bring electrical conductivity and for reducing the melting point of alumina. I repeat it again. In metallurgy of aluminium, purified Al2O3 mixed with Na3AlF6 and CaF2, which reduces melting point of alumina and bring electrical conductivity. Steel vessel with lining of carbon act as cathode, while graphite act as anode. The systematic figure or the apparatus used in metallurgy of aluminium is drawn on board. Here it is a copper clamp. It's a copper clamps. It is a terminal which is positive charge. It's a terminal which is negative charge. The electrodes are dipped in the mixture of Al2O3. Here the outlet for aluminium, it's a graphite rods which act as anode and steel vessel act as cathode, and this is the mixture of Al2O3, Na3AlF6, that is called cryolite, and feldspar CaF2. The importance of adding cryolite and feldspar is to reduce the melting point of alumina and bring electrical conductivity. The overall reaction take place in this setup is 2Al2O3 plus 3C gives 4Al plus 3CO2. The reaction take place at anode and cathode are: at anode, carbon combined with O double negative to form carbon monoxide plus 2 electron. Further, carbon react with 2 oxide ions to form carbon dioxide with elimination of 4 electron. At cathode, Al3 positive on gaining 3 electron give molten Al. The overall reaction for this apparatus is 2Al2O3 plus 3C gives 4Al plus 3CO2. This process is said to be Hall Haloroid process. This process is said to be Hall Haloroid process. I repeat it again. In metallurgy of aluminium, purified Al2O3 is mixed with Na3Al6 cryolite and CaF2, that is called fluorspar. These mixture we are adding purified Al2O3 with cryolite and fluorspar to reduce the melting point of alumina and also to bring electrical conductivity. Steel vessel with lining of carbon act as cathode while the graphite anodes are used. The overall reaction is here: at anode, carbon combined with oxide ion to liberate CO and CO2, and at cathode we will obtain aluminium metal. Now two questions arises. First is, what is the role of graphite rod in metallurgy of aluminium? Student, oxygen is liberated at anode, which combine with carbon of graphite to form carbon monoxide and carbon dioxide. If they are not present, oxygen recombine with aluminium to give back Al2O3. Now, next question is, what is the role of cryolite in the metallurgy of aluminium? Student, cryolite reduces the melting point of alumina and bring electrical conductivity. Thank you very much.